You probably think you know me from textbooks, right? Cold, abstract, a bunch of rules. But that's not really how I work. I don't just appear out of thin air in some perfect, tidy equation. No, I show up when things get messy. I emerge from chaos, from human need. I'm the language people invent when their world gets too complicated for the words they already have. And in 1665, my stage was set in London, and it was pure chaos. Death was everywhere. The Great Plague was ripping through the city, killing thousands upon thousands. London basically emptied out. Great universities like Cambridge bolted their doors, and life just stopped. And right in the middle of all this fear and confusion, a very quiet, very intense 23-year-old student got sent home. His name, of course, was Isaac Newton. He went back to his family's farm, totally cut off from everything. For most people, it would have been an ending. For him, it was just the beginning. So, while the rest of the world was fighting a plague of the body, I gave Newton a completely different problem to solve, a crisis of the mind. See, the universe is always moving. Planets are spinning, things are falling, everything is accelerating and slowing down, all the time. But how do you describe that? How do you use math to capture one single, fleeting moment of change? The old tools, the old math, it just wasn't going to cut it. To crack this problem, humanity was going to need a brand new language, a language built for motion, for a world that never stands still. And there, in that quiet farmhouse, I was about to give it to him. I started by giving him two new words. First, a fluent. That's what he called any quantity that changes over time, like the position of a falling apple. It flows, right? It's fluid. And then, the fluxion. That was the really clever bit. The fluxion was the rate of that flow, the exact speed at any given instant. This wasn't about static numbers anymore. This was about the physics of flow. So how did this actually work? Well, let's say your ball's position is a fluent, described by the equation s equals 5t squared. To find its speed at one specific moment, Newton looked at an infinitesimally small slice of time. He called it O. He'd figure out the average speed over that tiny interval. But here's the magic trick. He then imagined that interval, O, shrinking and shrinking until it became 0. And when O vanishes, all the fuzzy parts of the equation disappear, and you're left with just one thing, the fluxion, the perfect instantaneous speed, in this case, 10t. And that was it. That was the secret. He'd created a mathematical tool so precise it could slice up time and analyze a single instant. He could now describe not just where things were, but the very nature of how they were changing. This was the key that would unlock everything. So armed with this seriously powerful new language, Newton looked up from his notes and turned his gaze towards the heavens. It was time to take on one of the biggest, oldest riddles there was. You've heard the story. He's in his garden. He sees an apple fall. A totally normal thing to see. But it triggers this absolutely revolutionary question. Could the force that's pulling that little apple down to the ground be the exact same force that's holding the massive moon in its orbit hundreds of thousands of miles away? His train of thought was just brilliant. He realized the moon isn't just hanging up there, it's constantly falling towards the Earth. It's just moving sideways so fast that it keeps missing. So he reasoned, if it's the same force, it must get weaker the farther you get from Earth. He made a bold guess. Maybe it weakens with the square of the distance. Now all he had to do was see if the numbers backed him up. Okay, so he gets to calculating. First fact, the moon is roughly 60 times farther away from the center of the Earth than the apple in his garden is. So, if his inverse square idea was right, gravity's pull on the moon should be 1 over 60 squared, or 1/3600th, as strong as it is on the apple. That single number, that one tiny fraction, held the entire answer. He ran the numbers, he calculated how much the moon should be falling every second and compared it to the apple's fall, adjusted by that exact fraction. And they matched perfectly. It worked. And in that moment, the entire cosmos just snapped into focus. There weren't two sets of rules anymore. The laws that govern heaven and earth were exactly the same.
I mean, this discovery changed everything. Newton knew, he just knew, that he now had the tools to write the complete instruction manual for the universe.
But here's the thing about Newton. He was deeply, pathologically secretive. For nearly 20 years, these world-changing discoveries just sat in his notebooks. It wasn't until 1684, when the astronomer Edmund Halley came to visit and asked him about planetary orbits, that Newton was finally pushed to share his work. That question lit a fire under him. He worked like a man possessed for 2 years, and in 1687 he published his masterpiece, the Principia Mathematica.
And what a masterpiece it was. Inside, you had the 3 laws of motion, the law of universal gravitation. It explained pretty much everything. The strange elliptical paths of planets, the way comets streak across the sky, even the daily ebb and flow of the ocean tides. It was all there.
The poet Alexander Pope really summed it up perfectly. It was like someone had finally flipped a switch. The universe was no longer this dark, mysterious place. It was a machine, an intricate clockwork, and now, for the first time, humanity could understand how it worked.
But the story doesn't quite end there, because this incredible book, this explanation of literally everything, was hiding a huge, baffling secret.
I mean, think about it for a second. If this amazing new math, this method of fluxions, was the engine that powered all these discoveries, where was it? Why isn't it anywhere to be found in the pages of the Principia?
Well, it all came down to his personality. Newton hated being criticized. He was terrified that his newfangled methods would be attacked. So what did he do? He painstakingly translated every single one of his proofs back into the old, trusted language of classical geometry. He basically showed everyone the palace he built, but hid the revolutionary tools he used to build it.
He laid out the treasures of the universe for the entire world, but he kept the treasure map locked away just for himself. He was absolutely convinced that this incredible new language, this calculus, was his secret and his alone.
But here's the thing about me. I don't like to put all my eggs in one basket. Newton was sure he was my one and only chosen voice, but he was wrong. Because thousands of miles away, on the other side of the English Channel, I was already having a conversation with someone else. And that conversation, well, that was about to change the world all over again.